The breaker is closed, but the tripping coil will not be energized until either 1, the protective relay contacts close, or 2, the manual switching contacts are operated. In practice, there may be other parallel contacts which can open the breaker. Remember, the circuit breaker tripping coil and its auxiliary contacts are normally located at the circuit breaker inside the cabinet. This is probably in the switch yard, some distance away from the relay panel. However, relay operating contacts are located inside the relay. The manual switching contacts are normally located on the control panel. Now, when the relay operates due to sensing intolerable conditions, the relay contacts will close, and this now energizes the breaker tripping coil. This in turn causes the breaker to open and also causes the auxiliary contact to open, so breaking the DC tripping circuit. But it is possible that the relay contacts may bounce open first as the fault is removed by opening the breaker. These delicate contacts inside the relay are not made to interrupt this relatively high current flow through the tripping circuit. So in order to protect the contact surfaces, a seal-in arrangement is usually wired into the relay. It functions like this. When the tripping circuit is energized, the seal-in contactor switch is also energized by the passage of current. This in turn closes the seal-in contacts here, and they will remain closed as long as the circuit remains energized. Now, if the relay contacts open first, they will not interrupt the tripping current, as the closed seal-in contacts provide an alternative path. Only when the breaker auxiliary contact opens will the circuit be de-energized and the seal-in contact also opened. When working with protective relays, it is always essential to keep these two circuits separate in the mind. First, the relay itself functions according to the inputs being fed into the relay. Secondly, when the relay does operate, it closes its operating contacts, thus completing an external circuit, that is, the DC tripping circuit of the main breaker. Relays are often tested in place so that the total circuitry can be checked as well. Alternatively, they can be removed from the casing and placed on the test bench for test and calibration. When you remove a relay from its case on the panel, you can see the base contacts. These are providing input from the VTs and CTs or other sources to the relay sensing circuit, and also are providing a continuity of the breaker trip circuit. When the relay is removed, it is always necessary to open the circuits of the incoming VT and to disconnect DC to the relay. Conversely, the CT connections must be shorted. I'm sure you already know why this is so. If the secondary of a CT is open-circuited, when current is flowing in the primary, a very high voltage would arise across the secondary terminals. Of course, the circuit that we have been studying is extremely simple, and we have not specified any particular type of relay. You know that this is going to get far more complicated as we go along. For example, considering the three phases of the same circuit, we now have to include 3 relays, 1 per phase, plus a ground relay, all with their separate CTs and sometimes VTs as well. But before we go on, let's take a short break. Please switch off the tape now and thoroughly review this material in your workbook. Let's look at our simple protection circuit again. In order to identify the components, we have had to write the names of the devices on this diagram. An easier way would be to use a standard code or numbering scheme. This is especially important when we come to complex diagrams like this. Well, it just so happens that the American National Standards Institute, in collaboration with the IEEE, have provided a standardized list of device function numbers. These are used throughout North America and indeed in many other parts of the world. The list is quite extensive, numbering from 1 to 94. For example, quickly running your eye down the list, we find a master contactor, synchronous speed device, distance relay, field circuit breaker, AC circuit breaker, ground detector relay, rheostat, frequency relay, line switch, and so on, all with their respective numbers. The circuit breaker is represented by number 52, so we can place this into our elementary diagram. And supposing the protection relay is an AC directional overcurrent relay, this would be device number 67. In addition to device numbers, a list of abbreviated letters are also provided. And here we can see just at random that A is an abbreviation for alarm, CS represents a control switch or contactor switch, G indicates ground or a generator, N stands for neutral, TC for trip coil, and so on. Now, there is no need for you to remember all of these abbreviations or device numbers. A list is included in your workbook. But as you probably know from experience, you soon get accustomed to certain numbers, especially those referring to protective devices. Every time you look at a schematic and see the number 87, you know that this refers to a differential protection relay. In this case, differential protection across the primary and secondary of a transformer. What else does the diagram tell us? Well, we can see that the primary is delta connected and the secondary is Y grounded through a resistance. The circuit breakers are represented by 52P primary and 52S secondary. What do these other device numbers represent? Looking up our reference list, we find that the transformer itself is equipped with a thermal relay, 49, and a gas pressure relay, 63. This is a commonly used symbol for a CT, but please make sure you are familiar with your own company standards. This CT is installed in the neutral to ground connection, measuring ground current. It feeds time over current relays, 51G. Another time over current relay, 51, is installed on the secondary output before the breaker. And what is this on the primary, device number 50? An instantaneous over current relay. Well, now, before you get too involved in this circuit, remember, our objective here is not to discuss the settings and coordination of these relays, but rather to get ourselves thoroughly familiar with using electrical diagrams. Now, I know many of you are doing this every day, but not everybody is so fortunate, so please stick with it. Here is another simple protection diagram. A generator connected directly to a bus through circuit breaker 52G. You can already recognize some of these device numbers. 51G is a time over current relay in the neutral to ground. 87G, a differential relay across the generator. What is this 46? A negative phase sequence relay. 51V is a voltage-restrained time over current relay fed by the CT in the generator output, and a voltage transformer, which also feeds a directional power relay, 32, and a loss of field relay, 40. In studying these diagrams, it is essential to note the location of the source of